Hello everyone. So what do you mean by a carbanion? So basically, carbanion is a trivalent carbon species with a lone pair of electrons and a negative charge. Means carbon having 3 covalent bonds and a lone pair of electrons and a negative charge. Its shape is pyramidal. And hybridization is sp3. Okay. But the question is it always pyramidal? The answer is no. If the carbanion is going to be in conjugation with -m groups, then quite naturally the electron pair need to be delocalized, implying a planar structure. Therefore, conjugated carbanions have a planar structure, undergoing a rehybridization of sp2. That is, unconjugated carbanion will be having pyramidal shape, whereas conjugated carbanion will be planar with sp2 hybridization. So if we take the simple methyl carbanion, it is isostructural and isoelectronic with ammonia. That means methyl carbanion will have same number of electrons and also similar structure. Now let's move on to the stability of these carbanions. So what factors will stabilize the carbanion? This is very important aspect. Stability of carbanions. So what factors will stabilize the carbanion? So basically, carbanion is negatively charged species. So therefore, any factor that is going to disperse this extra electron density will stabilize the carbanion. So therefore, electron withdrawing groups or electron withdrawing groups, EWG. So electron withdrawing groups will stabilize the carbanions. Let us start with -I groups. Like NR3 plus, SR2 plus, OR2 plus, all positively charged species, and the halogens will stabilize the carbanions extensively. So greater the electron withdrawing ability, higher will be the stability. So therefore, quite naturally, the trifluoromethyl carbanion is more stable when compared to the triiodo or trichloromethyl carbanion. Whereas -I groups will destabilize the carbanion, +I groups will destabilize. +I groups will destabilize the carbanion. That's the reason why, look at here. So this is one +I group. So take the secondary carbanion. It is having 2 +I groups. Take tertiary carbanion. it will have 3 electron releasing groups. So stability decreases as the electron releasing groups are added. This is exactly reverse of what we have discussed in the stability of carbocations. The stability of carbocations is in the reverse order. So here carbanions, primary carbanion is more stable when compared to secondary, when compared to tertiary. This is for the carbanions. This you must keep it in mind. The second aspect that is going to decide the carbanion stability is conjugation. So all minus M groups so invariably contain heteroatomic multiple bond. So therefore, if the carbanion is adjacent to such groups, will stabilize the carbanion extensively, like NO2, cyano, carbonyl, etc. Even the adjacent pi bonds, that is C double bond C or C triple bond C, can also stabilize the carbanion. That's any group that is going to dispose the negative charge by means of conjugation is going to stabilize the carbanion, adjacent carbanion. Look at here. So greater the number of such a type of groups, higher will be the stability. So here you need to remember one thing. This is also called as acidic hydrogen, where X is equals to electron withdrawing group. Could it be minus I? Could it be minus M group? So why? Because this will withdraw electron density from carbon. Further, this carbon, this entire group will pull the electron density towards itself, making the CH bond weak, resulting in the release of the hydrogen as proton. The driving force for this is the minus I effect of this total group and also the stabilization of the resultant carbanion after generation. Suppose if you take nitro group or carbonyl group or sulfonyl group, whatever it is, the resultant negative charge will be stabilized by those groups. For example, if we take acetoacetic ester, these protons, that's methylene protons, are very much acidic because it is this carbon is flanked by 2 electron withdrawing groups. Number 2, the negative charge generated on this carbon will be stabilized extensively by this carbonyl and also this carbonyl. So such type of hydrogens, we call them as acidic hydrogens. Then third factor that is going to decide the stability is hybridization. Look at here. So hybridization of carbon here is sp3, it is sp2, it is sp. Then S percentage is 50%, 33%, 25%. We know that greater the S percentage, higher the electronegativity. So electronegativity of sp hybridized carbon is more when compared to sp2, which is higher than sp3. So naturally, so greater the electronegativity, higher will be the capacity to stabilize the generated carbanion. That is one. Even prior to that also, the hybridization, the electronegativity of that atom will make the SpCH more weak, means making that H more acidic. So therefore, the stability of this one is more than this one. The stability of vinyl is greater than stability of the ethyl carbonyl. And in all the ethynyl carbanion is very much stable when compared to the rest. Then you also have the adjacent third row elements. So third row elements, what are those? Particularly in organic chemistry you will encounter most of the times. If it is going to be either silicon or phosphorus or sulfur, then that is going to be very much stable. For example, if you take this is very much stable. That's the reason why this dithion, 1,3-dithions are extensively used as the so here look at here. The stability of this one is more when compared to this one. In fact, this is not at all generated. This could not be generated. This is a carbanion. Yes. So because the sulfur can stabilize this carbanion by means of delocalization. Because sulfur or phosphorus or silicon, they have the empty d orbitals. So because of this empty d orbitals, they will stabilize the resultant carbanions very much. So then you have aromatization. To take, for example, you take look at here. Consider these hydrogens. The cyclopentadienyl system is very much acidic. This hydrogen is very much acidic. The reason is, so here once you remove this proton, it will generate a species which is aromatic, cyclopentadienyl anion. This is aromatic species. So if the generation of carbanion is going to be resulting in an aromatic species, that will be very much stable. Look at here. Suppose if you are generating a carbanion, it will result in an anti-aromatic species. This will result in a non-aromatic species. This is anti-aromatic. This is non-aromatic species. We know the stability of aromatic compound is more than non-aromatic compound, which is further stable, and the least stable is anti-aromatic. So therefore, this is very much stable, that is extensively stabilized by means of aromatization. If at all there is a possibility of getting the aromaticity, that structure is going to be very much stable. So next factor will be the, what do you call this, homoallyl conjugation. So look at here. So what is homoallyl conjugation? Usually for conjugation, we require alternate double or single, or there you can have the charge. So this is, we call this as conjugated species. So naturally, this is more stable when compared to the simple ethyl carbanion. Suppose, because this we call it as conjugated species, this is simple conjugation. But if you take in between an unsaturated system, that is a multiple bond, and the charged species, if there is one sp3 carbon in between, basically conjugation is broken as such. But this can be stabilized. This we call it as homoallyl conjugation. So this will simply, the total negative charge will be delocalized over, that is surpassing the in between sp3 hybridized carbon, the negative charge will be dispersed over these three carbons. Similar to that one, look at here. Suppose if the generation of carbanion is very much easy here, because this can also be in conjugation. So this is what is known as homoallyl conjugation, is a common term. That is conjugation between non-adjacent species, particularly with one sp3 hybridized carbon in between. Such a type of, this is very much stable when compared to the simple system like this. For example, R is there. This is not at all stable. When you compare this X species and Y species, X is stable when compared to the Y. Okay. Then finally, you will have even cyclopropyl groups. This we have also seen in carbocation stability. Cyclopropyl groups will also stabilize more when compared to the ordinary, that is simple alkyl species. This is because of the bent or banana bonds of cyclopropyl system. This is true only for the cyclopropyl systems. And even just now we have seen the adjacent what you call it as third row elements, even if they are with multiply bonded, like they're further stable like this. So this is very much stable when compared to even simple sulfur. Even though you have lone pair of electrons, this is very much stable. Whereas this is not stable. It's highly unstable. This is very much stable. Like this, that is a minus A effect, then minus M effect. You have homoallyl conjugation, aromatization, then third row elements, particularly sulfur, phosphorus, etc. Then you have what you call as aromatization. These are the various factors that can extensively stabilize the carbocations.